All right, we're back. It's getting late. It's been raining outside. All that doesn't matter because what we're curious to know is what the answer to this question is. Why does spectral tilt go up and down in this example rather than just straight down? And the answer is what the topic of the lecture is supposed to be about, which is resonance. So we're filtering the harmonics in the sort of underlying source signal in this complex wave by taking advantage of the phenomenon of resonance. So resonance effectively creates a series of bandpass filters in our mouths, is one way to look at it. And those bandpass filters are going to basically intensify some of the harmonics in the underlying complex wave, and they're going to dampen out the intensity of other harmonics. So if the original series of harmonics looks like this, which is kind of the pattern we normally see for various types of voice quality, they change or differ in terms of how steep this slope is, but basically you get a mostly intense fundamental, or H1, and then they decrease in intensity as you go up the frequency scale. If we put them through this filter, or this series of bandpass filters in our vocal tract, the series of harmonics has to basically conform to the shape of this filter in terms of their intensity, and so that we get an output that looks like this, where we're seeing the effects of multiple filters over the frequency range of the entire series of harmonics. So the cool thing is that when we generate wideband spectrograms is that they help us see the shape of this filter. We're kind of seeing this part of it when we look at a wideband spectrogram. If we are looking at a narrowband spectrogram, we get something more like this, which is nice, but it's a little bit trickier to see this broader filter pattern in it. So rather than filters, though, you might consider the vocal tract to consist of a series of resonators if you want to think of it in positive terms rather than in negative terms. And those resonators, like the filters, will have center frequencies and particular bandwidths. And those characteristic resonant frequencies of some particular articulatory configuration are going to be called formants. And we looked at this a little bit on the previous in the previous lecture, because we saw what, say, Pratt thinks the particular center frequency of a given formant is, and also the bandwidth for that particular formant. Pratt's making an estimate, though. This is basically a theory of how we're generating sort of the overall spectral shape of a particular articulatory configuration. Remember, for each given some shape of your vocal tract, it's going to resonate better for certain frequencies than others, and the ones that resonates best for are called formants, and we can see those nice and easily in a spectrogram. The formants are going to appear as these dark horizontal bands in a wideband spectrogram, each of which has a center frequency somewhere around here, and the bandwidth, which is essentially like this gray area surrounding that center frequency in the formant. This is me saying something like a schwa. And we'll hear it again. So this is, again, the lowest frequency formant is what we call F1. The first formant. The second lowest frequency formant is F2. The third is F3, so on and so forth, all the way on up the scale. If we look at the same token in a narrowband spectrogram, it gets harder to kind of pick out that filter shape. You can see all the individual harmonics, which is great if you want that. But it's harder to see the formant. So you can kind of see that these are a little darker than these. That means this is the range of frequencies that forms the formant, basically. This is F2, this is F3, but we're seeing the harmonics a lot better than the formants in this particular version of the spectrogram. So we're not normally going to look at those unless we have some other compelling reason to do so. We could also look at the same vowel in spectrum form. So it's just grabbing a small slice from the middle of this vowel, and we see that kind of combination of source and filter that I showed you a couple slides ago. So we get the source properties in terms of the underlying harmonics. The F0 here is about 160 hertz, so each one of these harmonics is about 160 hertz apart from the next one. So this is 160, this is 320, this is 480, this is 640, so on and so forth, all the way up the scale. Now, presumably, if we looked at this as the sound was coming out of my vocal folds, again, without having to worry about my head on top of it, This one would have the highest intensity, this one would have the second highest, this one would have the third highest, and then it would keep going down the scale like this somehow. This particular complex wave, however, has been shaped by the shape of my vocal tract filter, or the series of resonators in my vocal tract, such that we get this nice kind of broad wavy pattern on top of all these harmonics. And this first kind of big peak is where we see F1. F1 is in the, 320 to 480, sort of in the like 400-ish range. F2, it'll wind up being a little higher than that. So 640, 800, 960, 1120, 1380, or 1280, 1440, somewhere around 1500 we'll get F2. But these big, broad peaks are the formants when we look at these things in the spectrum form. Again, like with the narrow band spectrogram, it's not going to be super easy to pick out the formants here. It's easier to see it in a wide band spectrogram, but you can kind of get the sense of what's going on here. The harmonics, which kind of fit into the sweet spots of the filters, are going to be intense. The ones that do not fit into those sweet spots are going to be dampened out, and they're going to be weaker in terms of intensity. Okay, so we get that sort of pattern through the phenomenon of resonance. We talked about that in 341. We're going to talk about it again. How does resonance occur, and specifically how does it occur in our vocal tracts? Where we are going to expand on this from what we didn't do in 341 is we want to find out as well, why do sounds resonate at particular frequencies given the shape of our vocal tracts? And then also, how can we change the resonant frequencies of the vocal tract and make spectral changes in speech that make it sound like speech, basically. We're not going to get to these two today. It's late enough as it is. I will address those in the next lecture, though, or in actually the series of lectures after that, because there's a couple of different theories about how this actually takes place. For now, let's just focus on this first question: how does resonance occur? Okay, so resonance, to try to define it in some meaningful way, is a phenomenon you get. It's a physical phenomenon when one object is set in motion by the vibrations of another object. So generally, a resonating object is going to reinforce sound waves at particular frequencies by vibrating at those frequencies itself. And the reason it does that is because the resonating object is basically responding to the periodic pressures exerted on it by the sound waves that are coming out of that initially vibrating object. So let's say I have my hand over here that's vibrating back and forth, and then eventually it makes this other hand resonate, and they will resonate or vibrate back and forth at the exact same frequency if I can be coordinated enough to do this. So this one basically, through the medium of the air between the two objects, is going to push the other one around, and they'll be kind of working in concert with each other. I don't know. I'm not drunk, I swear. Normally I can get my hands to work properly together, but hopefully you get the idea of how resonance works at a very basic level. In the case of speech, we're not having to deal with our hands here. Instead, the mouth and then sometimes the nose are primarily going to be the resonators, and they resonate in response to the complex waves created by voicing. So you've got your stringed instrument down here vibrating at a particular frequency, and then you've got the body of your instrument on top of that in the form of your mouth or your nose, and that's going to resonate at particular frequencies. And we'll get to this in a lecture later, but it's cooler than music, as if music wasn't cool enough. But you can change the shape of your instrument as you play the song, basically. So you can change the shape of your mouth, or to a certain extent your nose as well, and get different frequencies to resonate depending on whatever you want to say, right? Okay, so cool. We're going to be looking basically then at the shape, size, and length of the mouth and trying to figure out how this works. Okay, so resonance occurs because sound waves get reflected. So if you think in sort of an abstract case or an idealized case, you can have a wave that's traveling through. Once a wave starts, it can travel through a medium indefinitely unless it runs into something. And so I've got this basic example of, say, somebody throwing a pebble into a pond. Say you're at the park and you just get bored and want to throw a pebble in there. It likes a little splash, and then you see the kind of ripples traveling away from the site of the impact going throughout the pond. And they will lose a little bit of energy as they go, because this would be like in a real situation. It's not going to be, an ideally impervious or an ideally frictionless medium, I guess. So they will lose some energy, but if the stone hits in there like hard enough, the waves could travel all the way to the shore, right? Potentially. And then at that point, something different would happen. But if they are just traveling without any obstruction to get in their way, they're known as traveling waves. And so I've got this example from many years ago now. It's hard to believe this happened over 9 years ago. But this is the tsunami from Japan, which was kind of the biggest wave that ever formed in my lifetime. So this is on March 11th, 2011. There was a magnitude 8.9 earthquake that happened just off the coast of Japan, and it was massively destructive. And what's kind of interesting for our purposes is that it generated basically the biggest traveling wave of all time, or at least, again, in my lifetime. So the way we know that is, so Japan's over here. This red star shows the sort of where the earthquake took place, the epicenter, basically. And then out in the Pacific Ocean, they have these buoys out on the surface of the sea that would bounce up and down in response to the waves going past it. So they're able to get specific location and timing information for when the wave created by the earthquake went past these buoys, and those positions are represented down here. They look like little waveforms with these kind of transient signals going through them. Actually, I've never spoken about this before when I presented this video. What's kind of cool is you can notice each buoy goes up and then it goes down. So it starts out at this position and then it pops up because of the wave, and then it goes down below where it started, and then it kind of ripples after that. But the big peak is just where the waveform goes through it. So you can see that here. I guess it's represented by this white wavefront here as it goes across the Pacific Ocean. And then as it goes, you will see it bump into things like islands and coastlines. So it's going to hit Papua New Guinea here, and it's going to kind of bounce back a little bit. It's going to hit the west coast of Canada, and then it's going to bounce back to where it came from. There goes California. There's Australia, New Zealand, so on and so forth. The Pacific is a very big place, and it's going to take a very long time for this initial wavefront to get all the way down to South America. I do remember this day when it happened, because I had friends who work in the Bay Area, and one of them, like several hours after this earthquake took place, they looked out and got a video of the wave front rolling in underneath the Golden Gate Bridge into the San Francisco Bay, which is amazing. So eventually it goes all the way around South America, and then eventually to the rest of the world until it kind of dissipates, right? But the thing I kind of wanted to point out before I got distracted by that discussion of the Golden Gate Bridge is that it bounces back, right? So you can see that kind of echo here, as it were, bouncing back from the west coast and going back the other way. And we kind of get this interesting kind of interference pattern where we got some of the waves going one direction and the other waves going in the other direction, and they kind of like mix and match with each other in concentric circles. Yeah, so waves can bounce. I've got another video, which I don't play in 340 but kind of gives you an impression of the magnitude of this thing. I'm not going to make this too loud. Yeah, so this is basically, I think, the seismic signal of this earthquake, and it shows you basically a spectrogram derived from that seismic signal. So it's speeded up 100 times faster than its actual speed was, but I'll let you listen to it. Yeah, so that's what a magnitude 8.9 earthquake sounds like underneath the ocean. And you can hear it's basically the crust of the earth cracking. Yeah, so it keeps going, which had to be awful for the people who were involved in it for multiple reasons. The only earthquake I ever experienced was a Northridge quake in '94 when I was in school in Southern California. It occurred in the middle of the night at 4:31 in the morning. I'll never forget that time because it woke me up and I looked at my clock and memory burn. And we were far away from it. We were for like 35 miles away from it. We could still feel it. And there's woke me up out of bed and shook things around in her room a little bit. Didn't get hurt, nothing got damaged, but it was scary because I'm just a kid from the Midwest at that point in my life anyways. So the other scary part of it was the aftershocks, which, they weren't as strong as the original, but you kept feeling them throughout the day, and every time they would just make you worry, like, oh, is this happening again? And then you get the sense, like, is that an aftershock or is that not an aftershock? I don't know. Anyways, that was a destructive earthquake in LA. I can't remember how many people died, but there were a fair number of people who died, and there's a lot of damage. That was 6.6, but each one of these aftershocks is basically 6.6 or stronger. And this is a logarithmic scale, so like 7.6 is 10 times stronger than a 6.6 earthquake. So that is just kind of incredible to think about. Thankfully for us, it's 9 years in the past, and we have totally new disasters to worry about, as we know. So I'll just move on and remind you that the point of all that is that waves can get reflected. So if a wave encounters resistance, if a traveling wave encounters resistance, it will be reflected, and then what happens to the wave depends on what kind of resistance it encounters. So if the wave meets a hard surface, it gets a true bounce, and compressions, which we've talked about before, areas of high pressure in a waveform, they will come back as compressions, and rarefactions will come back as rarefactions. And like thinking about that in terms of the buoys that we saw before, it's a little bit different for these waves because blah, 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 blah. Yeah, so with these waves, it's more about vertical position in terms of the waveforms. So this means higher in the vertical world and lower in the vertical world. For sound waves, it's just variations in pressure. So it's either more pressure is high and lower pressure is a rarefaction. So the way it works with sound waves, the kind of default basic example is to think about a loudspeaker projecting sound into a closed tube. So we have a loudspeaker at this end, which is like our vocal folds, and then we have a closed tube at the far end. So this is like me closing my mouth and phonating briefly without trying to go through my nose. Yeah. Nowhere for the air to go. So if this loudspeaker pushes a pulse of air, a high pressure pulse through the tube, it travels down the length of the tube. This is time going in this direction. So time 1, time 2, time 3. This pressure pulse will travel. It'll be a traveling wave for a while until it gets to this far end, and then it bounces, and then it'll start coming back in the opposite direction. And so what you have to pay attention here, the maybe not totally intuitive thing, is that when you push this high pressure pulse down the length of the tube, what forms behind it is a rarefaction. So when this guy reaches the far end of the tube, all of a sudden we have less air pressure at the sort of initial end of the tube. And then that rarefaction itself will start traveling as well down the length of the tube. So this is how we get that kind of interesting pattern of interference between the compressions and rarefactions of this sound wave. So the pressure pulse goes this way, and then when it bounces back, it briefly, for a moment in time, will meet up with the rarefaction, and they'll cancel each other out. And this will be kind of equal again. And then the compression keeps going all the way back to the loudspeaker. The rarefaction goes to the opposite end, and kind of keeps changing places as they go. Okay, so if we're thinking about this, let's say we put a microphone down at the far end of the tube and wanted to record how air pressure was changing over time. We might get a readout like this. So let's say we just push one pressure pulse from the loudspeaker through the tube, then air pressure will increase at the far end of the tube, and then when that rarefaction comes in, it'll decrease to this bottom. And then it'll go back up when the compression comes back, and then back down the rarefaction. But one thing that's interesting is that that pressure pulse will lose energy over time, just because some of it gets sucked out through friction and the walls of the tube, and it can't just perfectly last forever, right? So this initial pulse, this initial peak will be higher than the second peak, so on and so forth. So it's like, boo, and it dampens out. So what would happen if, say, we sent another pressure pulse through the tube right when the initial pressure pulse gets back to the loudspeaker? And I don't think I really have the arrow in the right spot there, so I'm going to just erase that. But let's say this is my wall, my tube, this is my loudspeaker. I push, and it goes here, and it comes back, and it gets back to the original spot, and I push again. What happens? It's like if you push your kid sister or your kid brother or whatever, some child, on a swing at the playground, and you push them, and then they go over there, and then they come back, and you push again. What happens? They keep repeating the cycle, right? Same thing if you wait for that pressure pulse to come back and push with the loudspeaker again, the whole pattern will get repeated, and you will eventually get an interesting phenomenon known as a standing wave, which this kind of represents. It's where you get sort of alternations in pressure at different spots in the closed tube. And it will look like a waveform which is not traveling, but just kind of staying in the same space the whole time. You'll get those alternations between high and low pressure consistently as long as you keep sending in those pressure pulses at the right time. It'll no longer look like a traveling wave. It'll look like a standing wave. Okay, so this is what we get when we have resonance. And I've got this example of the Tacoma Narrows Bridge, which I show in 341. I'm going to show it again because it's a classic. And again, this might be, YouTube's copyright filter might defeat this. Hopefully not. But I'll show it to you anyway. So this is the bridge that was created in Washington State with materials that were too light and flimsy and cheap for the windy conditions in which it was created. So this is a good reason why you should not save money, is because you don't want your life's work to function like this. You can see here, this is a standing wave. So there's kind of a spot in the middle where it's not moving much. And then the sides of it are waving up and down. They tried to put cars on the bridge to kind of dampen out the vibration. But you get the same sort of thing here. Like in the middle, we're seeing not much motion. Well, okay, a little bit. And then on the sides, it's bouncing up and down. So it's not really traveling through the bridge. It's just kind of sticking around, which is going to cause a lot of problems for the material and structural integrity of the road surface, right? Somewhere in here, we get Professor Farquharson, as usual. An academic tries, but fails to save the day. Or maybe he gets a dog in a car. I never found out the answer to this story. Let's pretend he did, because why not? He looks like a nice guy. Actually, he looks like Martin Heidegger, the philosopher. And yeah, he's not drunk. He's just holding a pipe. Anyways, eventually the worst happens somewhere because the bridge can't handle it anymore. Boom. And they don't build bridges like that anymore. And I've never been down to the Tacoma Narrows, but someday I will, to see what the new one looks like. That was in 1940, I believe. I want to go back to this little part and just kind of reemphasize, looking at the kind of the crosswise section of this. There's a spot here that's not moving, and then there's also, like at the stanchions, it's not going to move either, right? But in the middle, there's two different spots where it is moving kind of to the maximal extent. And when this one is up, this one is down. When this one's up, this one's down. Right? So that's what the standing wave pattern looks like. Okay, I've got another example of that. Actually, I've got two examples. This one I also got from YouTube somewhere. This one's from Calgary. Yeah, so go ahead and make fun of the Americans all you want. It can happen to you too. As we know, it's often windy in Calgary. I think it's somewhere by the airport, right? Second. Yeah, so isn't that exciting? And I've got one other example of what are called lenticular clouds. So one of the things I really do like about living in Calgary are these cloud formations. Um, maybe that's one of those interlinguistics example sentences that nobody's ever said or heard before. But either way, I do like cloud formations in Calgary. So one particular kind of cloud that I like is called a lenticular cloud. So lenticular, this is derived from a lens. These clouds kind of look like lenses, and I'll show you an example here in a second. But they're formed in a very special way because we have the Rocky Mountains so close. Wind can bounce over the Rocky Mountains, and then it kind of forms a standing wave pattern where we're getting the kind of that bounce as it goes over the plains. And when the wind bounces up in response to the push by the mountains, it cools. And as it cools, the water in it will condense. So we get this interesting phenomenon such that the wind is kind of blowing in some particular direction, and then it forms clouds in particular spots as it goes. So instead of the clouds like normal being pushed by the wind just kind of goes through the clouds. Yeah, and it looks really cool because they kind of have this smoothed off edge appearance. Yeah, and then as they come back down, the wind warms up, and then the cloud goes away because the condensation can't stick around. Yeah, so this is another example of a standing wave. Let's see. I made a video of this. Like I said, I was kind of fascinated by these when I first moved here. So this is about 10 years ago. I like the Calgary sunsets as well quite a bit. So this is looking towards the Rockies. So this is north over here, more or less northwest. And this is south on this end, and the wind's going to blow from north to south. And then we get these cloud wave patterns. And it's nice when it's lit up by the sunset too. So the wind is just basically kind of flowing through these spots, and it creates clouds as it goes. And the clouds just stick around and change colors thanks to the sun. Everybody gets involved for the sake of unintentional art. Okay, so that's the fun stuff. Those are standing waves. I'll give you some terminology for standing waves. So I pointed these points out in the Tacoma Narrows video, but a node is the position of zero pressure change in a standing wave. So like in the middle spot of that bridge, this is the spot that's not moving up and down. In terms of a sound wave, we're going to see this basically in the middle of a closed tube. Because at the far end and the near end, we're going to get alternations between high and low pressure, but where they kind of meet up and cancel each other out is the node right in the middle. If you want to have a term to refer to those other spots where you get the maximum pressure changes, then surprisingly, these are going to be called antinodes. So an antinode is a position of maximum pressure change in a standing wave. So just keep that in mind. Those can be handy for later. What I want to end this lecture on is a basic first attempt at figuring out what sort of frequencies are going to resonate in a tube setup like this. So a standing wave can only be set up in the tube if the pressure pulses are emitted from the loudspeaker at the appropriate frequency. Remember, it's like pushing the kid on the swing. You got to have the pushes come at the right time. So what frequency is that going to be? You can think about that abstractly or in the sort of more formal sense, but I'm going to give you a specific answer with a specific example on the next page. The things you need to keep in mind for this are, number one, how fast sound travels through the tube, and then also, secondly, how long the tube is. Because that's going to determine how often you're going to be able to keep pushing and get the resonance pattern set up in the closed tube. So I'll answer the first question for you, which is how fast does sound travel? This isn't exactly correct. It's actually something like 343.1 meters per second. And it varies depending on what the temperature is, but we don't care about that stuff. We're just going to say the speed of sound is 350 meters per second to round it off a bit. And that converts to 35,000 centimeters per second. It may be useful to use centimeters here in some of our examples. If you want this into sort of like how fast is your car go speed, then it's 1,260 kilometers per hour. Or if you're a stupid American like me, that's 780 miles per hour. That's the speed of sound. So when they finally did break the speed of sound when they're traveling in airplanes and jets through the air, Chuck Yeager back in the day, they were going pretty fast, and they still can go pretty fast. Anyways, why we have to worry about this is that to get resonance in a closed tube like this, we want to push a pulse of air, have it travel the length of the tube. It's going to bounce and then come back to the loudspeaker, and then we're going to push again. So we have to figure out what the timing is such that we push the second time right at the same time that this pressure pulse comes back to the loudspeaker when the kid returns on the swing. Okay, so let's say that the length of our tube is a ridiculous 175 meters long, and for some reason we have a 175 meter long tube with a loudspeaker at one end, and we're pushing air pressure pulses through it with the loudspeaker. So 175 meters is a long ways. It's almost twice as long as a football field. But let's just use our imagination because it's going to make the math easy. So how often should we push in this particular case? What should the frequency of our pulse pushes be to get this whole system to resonate? Well, like I said, I'm trying to make the math easy. It's going to be about as simple as possible. What we have to do is go twice the length of the tube. Remember, we're going to push here, and the pressure pulse is going to travel all the way down the length to the closed end and bounce and come back. So that is a length of 350 meters. We just said, for simplicity's sake, that the speed of sound is going to be 350 meters per second. So it should take a sound wave 1 second to travel the length of the tube twice and come back to the loudspeaker. So how often or how long do we have to wait in between pressure pulses? We have to wait 1 second for the sound pressure peak to come back before we push again. And if our period is 1 second, then we're pushing once every second, right on every second. Our resonant frequency is going to be 1 hertz. That means we push once per second. That is the basic math of how this works. I am going to kind of expand this into a more formal notation next time so that we can more easily generalize this to more complicated conditions. But that's basically what we're doing when we create resonance in a tube is we wait for these pressure pulses to come back to where they started, and then we're reinforcing them so we get a standing wave pattern. And that takes a certain amount of time that we can conveniently calculate. So expect more math next time. In fact, next time is the most math we're going to do in this class, so be ready for it. All right, see you then.